So today we are very happy to have Juan from IAS, and he will tell us about the magnetic black hole. Please.
Okay, hello everybody. I hope everyone is doing okay. So I'll be talking about magnetic black holes, and this talk is based on a paper that I recently wrote, and it's really an expansion on some comments on some previous paper that was doing something else with this magnetic black holes that I'll discuss at the end, perhaps. So the goal would be to discuss some aspects of magnetically charged black holes in the standard model. Now, motivation is that magnetic black holes are long-lived configurations compatible with the laws of physics as we know them, provided the U1 gauge group of the standard model is compact. And maybe they were produced in the early universe, and for that reason, they are interesting primordial black hole candidates. Of course, people discuss primordial black holes mainly for uncharged black holes, but these magnetically charged ones are pretty interesting. And I'll discuss a little bit towards the end how they could have been created in the early universe. We should understand, and if they exist, we should understand their properties if we want to discover them or rule them out and so on. And they have interesting properties because they can have very large magnetic fields. Now, what are these interesting properties? Well, first, they are a natural way of getting very large magnetic fields. So natural in the sense that it's theoretically natural to generate magnetic fields that are stable and they don't decay. And also natural because they exist according to the laws of nature as we know them. They can exist. So one feature is that these magnetic fields can be so large that the electroweak symmetry can be restored around the black hole. And another feature is that also due to these magnetic fields is that the fermions, the standard model fermions, lead to a large number of effective fields going in and out of the black hole. And for that reason, the effects of Hawking radiation are greatly enhanced as compared to uncharged black holes. And finally, they can catalyze proton decay. So this is in a manner very similar to the Kallan-Rubakov effect for magnetic monopoles. Now, just continuing with motivation. So if you have usual Schwarzschild black holes that were created in the early universe, they would be evaporated by now if their masses were smaller than the mass of a mountain, or 10 to the 12 kilograms. Now, charged black holes can have masses bigger than the charge, and when they evaporate, they settle down to an extremal or very near extremal black hole, where the mass is proportional to the charge. So, and they can be very long-lived. Of course, they can be long-lived if the charged particles are very heavy, so that they cannot be pair created in the fields that are present in the black hole, and also if there are no other charged particles floating around. So for magnetic black holes, these two conditions are obeyed because if magnetic monopoles are heavy, let's say the heaviest they could be is roughly the Gatt scale. So if they're this heavy, they will live for a very long time. And also there are no nearby magnetic monopoles, so they can live for a long time. For example, you could have one of these magnetic black holes that weighs a few kilograms, and you could in principle carry it around. Now, of course, it would be very interesting to ask the questions of whether they could, well, first of all, there's the question of whether they could exist, and this involves the production mechanism and so on. And even if they exist, where the bound on their number is and so on. So these are all interesting questions, which if you wanted to answer, you would have to do step 0, which is to understand a bit their properties. And this talk will mostly be about the step 0 of trying to understand the properties of these black holes. So the starting point is the charged black hole solution. We'll discuss mostly extremal and near extremal black holes. So we'll, for simplicity, we'll start with the extremal solution, which you can see here. That's the extremal solution. It's characterized, the geometry is characterized by only one number, which is the radius or the extremal radius of the solution. This characterizes the size of the sphere in the near horizon region. So this throat here is representing the near horizon region and the fact that the sphere has some constant size there of order Re. The black hole has a magnetic flux, which is quantized in terms of an integer, Q. So Q is an integer, and the proper size of the magnetic field is equal to Q over R squared. So I would mostly include the factor of E in the magnetic field. So this is when you normalize the magnetic field so that its flux is an integer. Okay, so an important property is that the size of the black hole is related to the charge by this formula, which roughly says that the size of the black hole is proportional to the charge times the Planck length. And there were two scales that will be relevant for what we're going to discuss. And one scale is the size, and the other scale is square root of f. So f has units of 1 over length squared, and square root of f has units of energy. And this will be the typical energies of the Landau levels of charged particles that are moving in this background. So let me do a quick reminder of the Landau levels. So let's consider now constant magnetic field in flat space. So we have a situation as we are discussing here. We have the 1 and 2 plane, and we have the magnetic field in the third direction. And in this situation, we have boost invariance along the 3 and time directions, along the 3 direction. So then for all particles, we'll have some dispersion relation the following form. For the lightest levels or the lowest energy levels, we'll have the mass square, so the mass that we had in 4 dimensions. And then we have a contribution from the energies in the different Landau levels. So here we are considering the lowest Landau level. So for a scalar particle, so we have a scalar field, or spin 0. Then we have a positive contribution from the magnetic field. It roughly is related to the motion, energy of the motion of the particle when it goes around the magnetic field, when it's really in its lowest energy state, which has a wave function which is roughly localized within a region whose size is such that there is roughly 1 flux quantum flowing through that region. So that's the shape of the orbital. And well, you can choose orbitals of different shapes because these orbitals are degenerate, but you can choose them certainly to have this shape. Then if you consider a fermion, we have a massless fermion. Then you also have this orbital contribution, which is positive, but you can have a negative contribution due to the spin. So when the magnetic moment of the electron or the charged particle has a magnetic moment and can be anti-aligned with the magnetic field, and that reduces the energy, and it precisely cancels the orbital energy, so we have 0 here. Now this looks like a coincidence, but it's not. Well, you can give, let's say, high-level reason would be the anomaly cancellation. So the fact that if you had a massless fermion, then in 4 dimensions you would have a chiral anomaly. And if you dimensionally reduce this whole setup to 2 dimensions, you should also continue to have the chiral anomaly in 2 dimensions. And that is possible only if the effective particles you have in 2 dimensions are massless. So that's one rough way to understand the cancellation. But of course, it's very simple to directly do the computation and find the cancellation. For a vector, on the other hand, the magnetic moment is actually bigger because the vector has a bigger spin, and then the cancellation is actually, it over cancels, it's over screens. I mean, this effect is related to the fact that the beta functions for gluons have the opposite sign, but the net effect is that we have a reduction in the mass squared proportional to the energy of the magnetic field. And what this means is that if the magnetic field is very large, it could happen that this whole combination is less than 0. And if that happens, then we'll have an instability. And this will be an issue for the W boson. So W boson is charged, and if the magnetic field is bigger than the mass square, then we'll have this issue. Now so far we discussed all the lowest Landau levels, but we have further Landau levels with further spacings, which are in units of 2F. So we have one at 2F, one at 4F, etc. Now, how high is the magnetic field in our solution? So, well, the magnetic field had this expression that we discussed before. And so it's largest in a given solution near the horizon, where we have to put Q over RE squared. And when we use the expression for RE, we find that the magnetic field is inversely proportional to the charge. But of course, with a proportionality constant that involves the Planck scale, so this is very large when the charge is small. And as the charge becomes larger and larger, the actual proper size of the magnetic field becomes smaller. So even though the black hole has more charge, the proper size of the magnetic field is more diluted, and the actual proper size becomes smaller. So what that means is that if we start with a very, very huge black hole, very, very big black hole, the magnetic field will be relatively small. And then as we start decreasing the charge, there will be a point where the magnetic field becomes of order the mass of the W boson squared. And at that point, we'll have this electroweak instability we were talking about. This corresponds to, in ordinary units, to a magnetic field of 10 to the 20 Tesla. So very high magnetic field. Now, there are other issues. There are also changes in the QCD vacuum for lower values of magnetic field that I'm not discussing because those are a bit more complicated due to the fact that the QCD vacuum involves strong interactions. So we should keep in mind that there is a similar story to what we are discussing now, also for the QCD vacuum. But the one I'm going to discuss first is electroweak story, which is a little simpler. Now, okay, so that happens. So you can starting from this equation and the previous formula for F, you can calculate the charge for which this happens. So this is the charge. You can calculate the mass of the black hole of this charge, and it's a mass roughly of the mass of the Earth, and that is a size of order a few centimeters. So for this black hole, you will have this electroweak instability, and for black holes smaller than this, you will find a region where W bosons condense, and we'll discuss in a second what happens with this condensation. And so, but the point is that we can have a macroscopic object which where the electroweak vacuum is not the one we are used to. Okay. Of course, it's microscopic, but its mass is astronomical. So we expect that the condensation of W bosons screen the SU2 part of the magnetic field. So if the ordinary electromagnetic magnetic field is the combination of a hypercharged part and SU2 part. And initially, the two are equal to what we were calling F. But the idea is that if we have a black hole much smaller than the size of that pool ball that we were discussing, then the SU2 part will be completely screened in the near horizon region, and we will only have the hypercharged part. So let's first discuss what happens after we screen it completely. Then what happens is that the Higgs is charged under hypercharge, and that means that due to the Landau levels we discussed before, we'll have a positive energy contribution from the Landau level, and this drives the Higgs to 0 value. So it's convenient for the Higgs to not to have the non-zero expectation value that it has in our vacuum, but to have a 0 expectation value. And so we find that electroweak symmetry is restored for large magnetic fields. And this is something that was observed in the 90s and was studied in detail in papers by Ambjørn and Olesen. And I'll summarize what they found. So here I'm just repeating what we said before, that if we look at the Higgs potential for small values of the Higgs field, then there is the negative contribution, the usual negative contribution. plus the positive contribution due to the magnetic field. The factor 1/2 is because we are in these units where the weak hypercharge of the magnetic field is 1/2. And so these two become equal this value, which corresponds to the situation where the magnetic field is equal to the mass of the Higgs squared. And it turns out that in nature, the mass of the Higgs squared is bigger than the mass of the W. So as we start increasing the magnetic field, there will be two transitions, one having to do with the condensation of W bosons, and one having to do with the restoration, complete restoration of the electroweak symmetry. So what was found in this paper of series of papers of Ambier and Oleson, and also investigated a bit more by other authors more recently, is the following. So as you start increasing the magnetic field, there is a region with pure electromagnetic magnetic field. So here the BEV has the usual value and so on. When the magnetic field reaches the mass of the W, then there is a second order phase transition, and we start getting a mixed non-uniform in space phase. So of course the W boson has spin 1, so cannot condense in a completely rotational invariant fashion and so on. And not only that, but when this W boson forms, you get some vortices and some structure of that kind. So not translational invariant state. It's a bit similar to this Abrikosov lattices that you get in with the U1 Higgs model or superconductors. So you get that non-uniform phase, but when the magnetic field is large enough, then all the W bosons become 0. So all the SU2 part of the magnetic field becomes 0, and you only get the weak hypercharged part of the magnetic field, which is again uniform, and the Higgs wave becomes 0 again. So the Higgs wave goes from being non-zero on this side, and then here it decreases all the way to 0. And in between, the Higgs wave is not uniform in space. Okay, so that's the situation in flat space. And now we go back to the black hole case. And so in the black hole case, we expect a structure that we can call the Electroweak Corona. So we have a black hole at the center. And then we're imagining a black hole smaller than a billiard ball. So there will be a region near the black hole, this region here, where the Higgs wave is 0, and we have purely hypercharged magnetic field. And this will happen up to a radius, and where the flux becomes equal to the Higgs mass. And at this value, the Higgs will start condensing as we go out, and also the W bosons and so on will start condensing. And by the time we get to an R of order such that the magnetic field is equal to the W mass squared, then at that point we will have the usual Higgs wave, and all the W bosons will be 0 again, and we'll have a region outside with purely electromagnetic magnetic field. One interesting point is that the size of this Electroweak Corona can be much larger than the size of the black hole, because the size of the black hole sort of goes linearly with Q. The size of the corona goes like square root of Q, but with a coefficient. So here the coefficient is much smaller than 1 over MW, which is what sets the size of the corona. And then for this reason, there is a whole range of values of Q, where this one here, the corona radius, is much bigger than the black hole radius. Eventually, for very large Q, of course, the fact that this term is linear in Q will always win, and in that case, we don't have this corona. That happens for black holes bigger than a billiard ball. So this is the same expression of the two radii. So we have the radius of the black hole here, and then the radius of the corona here, which is bigger. This is a log-log plot, and this is the black hole here, where which has a size of order the billiard ball and the mass of the Earth. And so if you wanted to have a black hole which is a few kilograms, it will be sitting somewhere here. with sizes which are either in the size, which are roughly the size of a proton for the corona, and of course a much smaller size for the actual black hole. Now, in the same way that we could discuss this Electroweak Corona radius, we could define a QCD radius. That's the radius where the vacuum of QCD is distorted in an important way. Notice QCD around the ordinary vacuum, we have also spin one fields like the rho mesons and so on. And if the magnetic field that are charged, and the magnetic field, if the magnetic field is big, you can condense those, and that leads to, again, this QCD radius, which is a bit bigger. I mean, it's bigger by the same ratio that the Electroweak scale is bigger than the QCD scale. Okay, so now I'll discuss some qualitative aspects of this Electroweak corona. So we could first consider a simpler problem, which is a magnetically charged black hole in the abelian Higgs model but plus gravity. Far away, we have the model where the U1 symmetry is broken, and the magnetic field is being carried by vortex strings, so the Nielsen nodes and vortices. And then near the horizon of the black hole, we have a whole region where the Electroweak symmetry, the U1 symmetry is restored and the Higgs value is 0. And this is what we would have in the standard model roughly if we remove the SU2 gauge fields. It's not exactly because here we had only one Higgs field, but we would have two in the standard model. Now, when we reintroduce the magnetic fields, what we have is basically that those vortex strings, roughly speaking, can end on these SU2 monopoles of the SU2 gauge fields. And it doesn't have precisely this shape, but it has a shape where these are more spread out. It's more similar to what we discussed before. But that's one way to more or less conceptually understand what's going on. Now, the solution where these W bosons and so on are not condensed is still a solution of the equations. And by condensing them, we decrease the energy of the black hole and decrease the energy of the solution. That means that the energy of the solution, or the mass of this whole configuration, is less than the mass you would expect for an extremal black hole just by noticing what the charge and mass are far away at infinity. And this is in agreement with expectation from weak gravity ideas that say that the black hole should be smaller than that there should be states with mass less than the extremal mass, and this is, for example, one of those such states. Now, I should emphasize that this corona I've been talking about is present for any localized magnetic source. It does not have to be a black hole. For example, a collection of closely packed magnetic monopoles would also display this phenomenon. And now, of course, if you just had lots of magnetic monopoles of the same charge, they would repel and they would fly apart. The black hole gives you a more natural way of having this localized magnetic field where you don't have to worry too much about it breaking apart. Now, there is one special case for Q equal to 2, when the magnetic charge is 2, when the solution is spherically symmetric. So for all other cases, the solution is not spherically symmetric, but roughly for the same reason that the strings we discussed or these vortex condensations are not translation invariant. And the solution was discussed by Cho and Mason, and it consists of a Dirac monopole for hypercharge at the very center of the solution, and then an SU2 monopole, which is a little bit spread out around the solution. Now for Q, and that has the size of order the Electroweak scale. For general Q, it's not spherically symmetric, as we said. Now this phenomenon of the corona and so on, it's not present for the Q equal to 1 GAT magnetic monopole, because in that case, we cannot remove the SU2 part of the magnetic field. So the SU2 part of the magnetic field consists of a kind of discrete flux, which cannot be removed by the W bosons. And also there is a discrete SU3 flux. And this is related to the fact that if there are particles in the standard model that have hypercharges in units of 1/6. So naively, one would have expected that Q should be a multiple of 6. And indeed, if Q is not a multiple of 6, we need not only a U1 flux, but we also need some SU2 and SU3 fluxes. And so in our discussion, we basically, in this discussion here, we are assuming the gauge group of the standard model is SU2 times U1 times SU3 divided by C6, as it is the case when the model comes from a GAD theory. Now, all these extra discrete fluxes we're discussing here are small compared to Q, so we are not going to discuss them anymore. And so for very large Q, we can ignore them. Or if you wish, you can take Q, which is a multiple of 6, and then they're exactly 0. Okay, so far we discussed some classical aspects of these black holes in the classical Electroweak theory. And now we'll discuss some more quantum aspects where we consider the fermions, the standard model fermions, propagating in this background. When we consider the region where Electroweak symmetry is restored, they're all massless. So even the top quark would be massless in this region. And they're all charged on the hypercharged hypercharged field. And so they all have a 0 energy Landau level. The degeneracy of the Landau level is proportional to Q, to the charge, and then also proportional to the hypercharge of the corresponding field. And then this leads to effectively two-dimensional massless modes that propagate along the radial direction. So these modes can be viewed as moving along the magnetic field lines, roughly one massless mode per flux quantum. Now you can go through the table of all the fields in the standard model and figure out how many left and right moving modes this gives rise to, because the representations are chiral. You have also in two-dimensional chiral fields that move either purely radially outwards or purely radially inwards to the black hole. And here we just noted the degeneracy. So the minus means it's moving into the black hole, and plus means it's moving out of the black hole. And this drawing here is representing what we were discussing, that each two-dimensional field is moving roughly along one magnetic field line, and the corresponding orbital has some size of order 1 flux unit. So as the magnetic field becomes smaller, the orbital becomes a little bit wider and so on. So now when this mode, so that was all in the region where the Higgs is 0. When we cross Electroweak Corona, some of them get some mass. Of course, some get more mass than the others, the top quark more than the electron, etc. And some become neutral, so like the neutrino. And if it becomes neutral, then you lose this large degeneracy of all the Landau levels. But for other cases, like for the electron, you will continue to have this mode that if we can neglect the mass of the electron, then we'll also continue to behave basically like a bunch of massless fields coming out of the black hole. Now, in principle, to find the proper infrared dynamics, we also have to consider the dynamics of the gauge fields, the U1, SU2, and SU3 gauge fields. And we have not discussed that, and we'll discuss a bit later the U1 case, and I will not discuss the SU2 and SU3 cases in this talk. So now we move on to the case of Hawking radiation. And so the evaporation of a black hole for a near extremal black hole goes, so the power emitted is given essentially by the two-dimensional black body formula. So it's proportional to the temperature squared, and Q is the number of fields that we have. So we have a number of fields proportional to Q due to this large degeneracy. Now, if we had a Schwarzschild black hole, which at the same temperature, so we would have the temperature to the fourth factor, and then the area would be like RS squared, radius squared, and that's proportional to 1 of the temperature. And so we get also something proportional to T squared. But we don't have the factor of Q. So that means that for black holes at the same temperature, these magnetically charged ones would evaporate more quickly. So for example, so let's give this example here. So imagine that we have an uncharged black hole of a mass of a mountain. So, and we have a magnetic black hole of the same mass. So for a massive mountain, it takes the age of the universe to evaporate using for an uncharged black hole. But if we had a magnetically charged black hole of the same mass, the evaporation time, or the time it would take to decay to extremality, timescale would be of order milliseconds. So it will decay exponentially to extremality, but with a timescale of order milliseconds. And in this case, for an order 1 deviation from extremality, the temperature is of order GeV, so the same as the temperature for the other case. And for these reasonably high temperatures, we expect we can perhaps ignore the effects of QCD, or they're not too important. Now, when T becomes smaller than the...
Juan, I think I missed something there. What is the mass and charge of the magnetically charged black hole that you're comparing to the uncharged one?
Yeah. So we have two black holes of the same, basically, radius.
Hello?
So we have two black holes of basically the same radius. So for the magnetically charged, so there is this black hole, right? And here I take a black hole of the same mass and with an order 1 deviation from extremality. What that means is that, let's say the mass is, let's say, twice the charge, for example. No, it's not equal to the charge.
Okay,
but
yeah, thanks. That answers my question. Thank you.
Yeah. Mm-hmm. And so it will have, because of this, it will have a temperature which is also of order 1 over, I mean, it will be of order RS again. I mean, up to factors of 2 and so on. I'm not keeping track of those factors. I mean, I'm not keeping track of those factors because the difference is very big in the lifetime, right? So black holes of, the point here is that the magnetic black hole of this mass would evaporate very quickly before, you know, before nucleosynthesis, for example. Okay, so as T becomes smaller than the electron mass, then there is an exponential suppression in the rate, the Hawking emission rate. Okay, you have to take that into account if you want. Now, black holes violate the global symmetries, and so that means that baryons can go in and leptons can come out, and so this would catalyze proton decay. And this leads to a fine application for these black holes, which is that, let's say you could have a relatively light black hole, let's say 100 kilograms, and then by shooting protons into this, you could generate, you could let them convert into leptons, and in this way generate energy. And if you can get enough protons going in, you could generate a significant amount of energy, let's say a megawatt. And now, in addition to this fact, this baryon number violation of the black hole itself, it seems that also Sphaleron effects are unsuppressed inside the corona, and also would lead to baryon number violation. So you don't even need to be all the way inside the black hole to generate some energy. Now, this can be compared and contrasted to the usual Kallan-Rubakov effect. So I remind you that the magnetic monopoles can also catalyze proton decay. And that's roughly because at the very core of the monopole, you essentially restore the full SU5 symmetry. Now, for this effect to be important, it was also important that the fermions are effectively behave like two-dimensional massless fields. So there is a particular mode of the fermions, sometimes called an S-wave, which behaves as a two-dimensional massless field and can get to the center of the monopole. Because if this hadn't happened, then it would be still true that maybe you can catalyze proton decay at the very center of the monopole. That very center of the monopole is very tiny. So the ordinary fermions would have a very extended wave function, and they would not have any overlap at this center, very small overlap. But the fact that we have this feature is what makes it possible. So roughly speaking, this effect guides the fermion to the very tiny region near the core where baryon number is violated. So here we have a conceptually similar effect, but it is enhanced by a factor of Q. So we have Q fields and so on. And another difference is that the baryon violation is not due to the grand unified theory, but due to black holes. Okay, so now let's discuss stability. So far we've treated them as essentially stable, but they're not actually completely stable. So they can decay by pair creating magnetically charged objects, and the rate depends on the mass of these objects. So they can be singly charged black holes like GAT monopoles, or they can be lighter magnetically charged black holes. And so the rate will be small if the mass is very large of these elementary charged particles. And the biggest expected mass is of order the GAT monopoles or a mass given by the weak gravity bound. So the weak gravity bound tells you that if you have 1 unit of magnetic charge, you should have a mass less than something, and that something is of order the GAT monopole mass, the GAT scale monopole. And this effect leads to so if the charge is roughly bigger than a million, so mass bigger than about a kilogram, they are effectively stable over the age of the universe. Now let's discuss a bit the production of these black holes in the early universe. So first, I will remind you of some mechanisms that people have discussed for producing uncharged black holes, so just ordinary Schwarzschild black holes. So these mechanisms, there are mechanisms involving large primordial fluctuations, or also phase transitions, violent processes after the end of inflation. So all of these are different mechanisms. So let's discuss the first one, because we will use a variant of that one later. And the idea is the following. So you start, during the time of inflation, you produce fluctuations in the primordial fluctuations, which have different amplitudes at different scales. So at, let's say, very long distance scales, the amplitude is small, but due to the particular form shape of the inflaton, the amplitude becomes bigger of order 1, let's say, at some scales, and then it might become small again at smaller scales. So if this happens after inflation ends and you enter in the Big Bang phase, at some point when these scales enter the horizon, you will form black holes of a particular size, a size associated to this particular scale, which had large fluctuations. And of course, the black holes will not be exactly equal to each other. There is some distribution, but you will tend to form black holes of specific masses. And so this is a mechanism that can by dialing the properties of the potential, you can make black holes of various masses. So people talk about making yeah.
Are you aware of any such model that solves another problem other than us wanting some primordial black holes to look at?
Not that I know. Yeah, this is sort of like a menu. It's like a little box that you put in, and you order the black hole. You have to pay a price, so they charge you a price of unnaturalness. So these are not natural models.
Yeah.
So yeah, it is possible. So no one can come and tell you it's impossible. But yeah, I would say it's not likely. But you know,
you have to get lucky. Okay.
Yeah, you have to get lucky, and yeah. So you already have to get lucky for getting this type of primordial black holes, and as you'll see, you'll have to be even more lucky to get the ones we're discussing. Okay, so if you thought that was unnatural, the one I'm going to discuss now will be a little more unnatural. So this is a mechanism which basically combines two previous mechanisms that people discussed in the literature. So I call it the square root of n mechanism. So the idea of this is the following. So let's say after the end of inflation, you produce a large number of monopoles and anti-monopoles. And then you have large primordial fluctuations at some scales. And then you produce a bunch of black holes that swallow all these monopoles and anti-monopoles. But they don't swallow a completely neutral, I mean, they don't swallow exactly the same number of monopoles and anti-monopoles. There are some fluctuations in the charges of the monopoles. So here in this region, for example, we have slightly more red ones or positive charged ones. In this region, we have slightly more negatively charged ones. And so we'll have some charge which, these black holes will have some charge of order square root of n. And then this black holes would evaporate and become extremal. So that's the idea. So the idea of getting monopoles and anti-monopoles into the black holes was discussed in this paper as a way of getting rid of monopoles and anti-monopoles. And the idea of the square root of n was discussed in this paper, which was attempting to create charged black holes for dark matter, electrically charged black holes for dark, charged under dark U1. Okay, and this is a point that, well, already Rafael was asking about. This is certainly not what we expect in the simplest model of inflation. It's not natural, but it doesn't seem outrageous. And there might be other mechanisms for producing them that are, well, they might be also unnatural, but maybe there are also other mechanisms. Now I promised we would discuss a little bit the dynamics of the U1, of the gauge fields, and I'm only going to discuss the dynamics of the U1 because it's kind of interesting, and there is an interesting relation to this other interesting theory called force-free electrodynamics, which I guess this is, well, it's a theory that is discussed in astrophysics, but it's interesting also for this problem and has some nice theoretical properties. So we'll discuss a problem of a gauge field in the presence of charged fermions. Okay, that sometimes people get confused and think that you could pair create fermions when the magnetic field exceeds a critical value. Of course, that's true for an electric field, but not true for a magnetic field. All that happens is that when the magnetic field becomes a fourth of the mass square, then the Landau level physics dominates. And so for us, we'll remove this mass term for now. So the Landau level physics dominates. We consider a problem where we have this large magnetic field. And as we discussed, the fermions move along the magnetic field lines. People have discussed recently something called fractals, where there are also particles that can only move along some dimensions of space, but not all of them. So in this case, we have fermions which move purely along the magnetic field lines. Now, we can analyze this problem by bosonizing the fermions in such a way that the corresponding boson shifts under the chiral symmetry. So, I mean, there is also the dual way of bosonizing it, phi and phi dual. And so we bosonize them in such a way that the coupling to the magnetic field is via this coupling. So one of them could be viewed as the background magnetic field, and the other one is the coupling of the fields along the field lines to the bosonized fermion. Now there is one bosonized fermion. There is one boson per unit magnetic field line. So there is we are summing over all the magnetic field lines, and that's roughly can be viewed as this integral. So these fermions are really two-dimensional, and they have a two-dimensional kinetic term. So along the d2x can be viewed as the dimensions along the magnetic field. And so then this is a continuum approximation to all these field lines. So we get effectively this four-dimensional action. And it turns out that at low energies, this term is irrelevant. I'm not proving it here, but I'll give you a different explanation later. And so then you find that the only effect of these bosonized fermions is simply to set f wedge f equal to 0, or e dot b equal to 0. So this is roughly saying that if you have an electric field along the magnetic field, that component of the electric field is immediately set to 0 because of the currents you generate due to this fermion. So if you have massless fermions that move fast enough that they screen completely the current. But so we get a theory which is just ordinary electromagnetism plus this extra constraint, and this is called force-free electrodynamics. And this is a theory that's been considered before in the context of plasma physics and astrophysics. It's a theory that describes these plasmas and so on when the magnetic energy dominates. And the derivation we just saw here is just a variation of one that was given by astrophysicists in the 90s, and Sam Graglia recently gave a derivation more along these lines. So there is a nice review on force-free electrodynamics by Gray and Thompson, and so I'm going to just mention it here. So as I just said, this for astrophysics is interesting. It's a classically conformal invariant theory, so but it's non-trivially interacting due to this constraint. You can solve the constraint by writing A in terms of two scalar fields, and then F would be given by this expression, and then F which F is would be 0 because there are only two gradients here. And if you do this and you insert into the Lagrangian, you get some Lagrangian which is nonlinear in phi, and it's well defined. It has only second time derivatives. It has more spatial derivatives and so on. It's some theory you could analyze. It makes sense classically. It has some symmetries of area preserving and so on. And you can think of these phi's as, roughly speaking, the Lagrangian coordinates of a string fluid. So I'm now going to basically say what we discussed before, but in terms of more physical excitations and not in terms of the Lagrangian, just perhaps to explain a little bit more what's going on with this theory. Everything that I'm reviewing now, it's been well understood, but I'm just reviewing it. So first, it's useful to consider the magnetic field and imagine that the gauge coupling is 0. So in this limit, we have two kinds of excitations. So we have the particles that move along the magnetic field that have a dispersion relation p squared equal to 0. So these are massless particles along the x correspond to the time direction and the direction along the magnetic field, and y correspond to the two transverse dimensions. And px and py are the corresponding momenta. And then we also have separately the two modes of the photon, so two polarizations of the photon that have the four-dimensional massless dispersion relation. Now, once E is non-zero, there is a kind of Higgs mechanism that Higgs is, roughly speaking, one of the components of the electromagnetic field. And so there is one field that is massive, so F is the value of the magnetic field. And so this is an effectively massive field. So if we consider to very low energies, we will not have it. And then we are left with two other mass excitations, which have a dispersion relation similar to the ones we had before. And it is these two excitations that are described by force-free electrodynamics. And this massive mode, the presence of this massive mode is related to that term that I mentioned that was irrelevant in the Lagrangian description. So saying that that term is irrelevant is similar to, well, I mean, and going to low energies is the same as neglecting this massive mode. So this explains a little bit more that force-free electrodynamics is the low energy theory of what we are discussing here, of the Landau levels. Now there is the following qualitative picture for what those two modes are. So I discussed these two modes that are described, the excitations of force-free electrodynamics. So we can think of force-free electrodynamics as being describing a gas of strings, so some collection of strings as we have here. And one of the modes, the one that is has a massless dispersion relation in 2D, corresponds to transverse oscillations of these strings, some shear non-compressional modes. And these ones here, the other ones, the ones that have this dispersion relation correspond to compressional modes of the string. So oscillations along the string, but there is some compressibility, and you can think of this as related to the compressibility of these strings. Now you can change the coefficient by changing the Lagrangian from f squared to some function of f squared. For example, you can take the Dirac-Born-Infeld Lagrangian. So you get the theory of force-free Dirac-Born-Infeld. And if you take f very large, then you find that this coefficient becomes 0, and there it becomes more closely related to a gas of strings. And this theory is, well, of course, it's connected to plasma physics, affluent waves, and so on. And it can be viewed as a theory connected to one-form symmetries, and is basically describing the pattern of symmetry breaking of a magnetic one-form symmetry. So just the ordinary electromagnetism is describing theory where you're breaking both an electric and a magnetic one form symmetry. Here you just have purely a magnetic one form symmetry. Now, this discussion helps building the intuition for one result that is interesting related to these magnetic black holes, which is the following. So in ordinary electromagnetic theory, you can have, and gravity, you can have a rotating Kerr-Newman black hole. And that black hole, if it initially rotating, it will stay rotating for a long time. But here, due to the fact that in the regime where you can describe it using this force-free electrodynamics, that is in the regime where you can neglect the mass of the fermions, or within the region of the electroweak symmetry restoration, then if you had a rotating black hole there, it would emit energy, even though it's a stationary situation. And one way to understand why it's emitting energy is that these magnetic field lines of the force-free theory are behaving a bit like strings. And if you had a black hole attached to strings and the black hole is rotating, it would stretch these strings, and it would these strings would remove the they would remove the rotational energy of the black hole, and there would be an energy flow to infinity. This is one way to understand it. Of course, you could say you have magnetic fields, and then because rotation, you have some electric fields, you have current, and then you have some transfer of energy. So it's not completely unexpected. And in fact, this mechanism is essentially the same, and it was originally discussed by Blanford and Senyak to be in the context of astrophysical black holes, in the context of understanding how rotating black holes in the center of galaxies manage to extract energy. I mean, manage to give energy to power jets and stuff like that. Okay, so the conclusion of this story is that we expect these black holes to be charged, but essentially non-rotating, because they would lose energy very quickly. So in conclusions, these magnetic black holes are interesting objects in the standard model. They naturally have very high magnetic fields. We can restore the electroweak symmetry in a relatively large region. So this region called the magnetic corona is much bigger than the black hole, and it could be even macroscopic size. It leads to interesting effects for Hawking radiation, and there are interesting candidates for primordial black holes, and so on. Now, there are two extra points that I have not discussed. One is that we can use them to construct traversable wormholes. So you can take these black holes and put them sufficiently close to each other, a pair of them, and construct a traversable wormhole. They are very tiny, so they are not useful for science fiction. I mean, they're not useful for sending a human, but they might be useful for sending elementary particles. The other point I wanted to emphasize is that these 4D black holes are also well approximated by very simple two-dimensional toy models of gravity plus a two-dimensional CFT, and these toy models have been recently discussed, starting from this paper, for discussing various aspects of black holes. And you can say, oh well, these were very artificial toy models, but in the context of these near extremal black holes, the actual physics of the four-dimensional black hole becomes essentially that of these two-dimensional toy models. The reason is that most of the fields correspond to this to a large number of fields, which are essentially two-dimensional in character. They just move along time in the radial direction. And in the near extremal limit, the main gravitational degree of freedom corresponds to the degree of freedom described by the two-dimensional gravity, so two-dimensional Jakob-Teitelbaum gravity. Now, there are many questions that one can discuss in the future. So I think there are interesting phenomenological questions, which one is to find more production mechanism, and the other is getting some constraints from astrophysics of how many of these black holes could be there. I mean, there may be a bound on these black holes and so on. I think often in astrophysics, we think about various exotic objects, let's say cue balls, cosmic strings, etc. And this is one other exotic. This is not so exotic. I mean, it's just part of the standard model. And I think it would be interesting to find what the constraints are. The constraints are probably somewhat similar to the constraints of magnetic monopoles, but different because they could have larger masses. So for some of the constraints, this is relevant. So. And then there are some more theoretical questions, which is to understand better the infrared dynamics nature with very high magnetic fields. Okay, thank you.
Thank you very much.
Thank you. Questions? So I guess I have one. Aside from the usual sort of constraints from astrophysics, are there any specific smoking gun type signals that would be characteristic of these black holes, at least in some range? Could we go hunting for them in some new way?
I don't know. Yeah, I don't know. Of course, there could be, radio waves emitted by particles trapped in their magnetic fields, etc. But I don't know enough about astrophysics to know what the best way to look for them is.
But sorry, isn't it one thing it's could be different from magnetic monopole is that is this guy still Hawking radiating or just completely static?
Well, if there is matter falling in, there could be Hawking radiating. So,
because in the usual primordial black hole, strong constraints come from like Hawking radiation, like destroying BBN and stuff. Like product of the Hawking radiation, it's just destroy nucleus and then also cosmic rays.
Yeah, that's
and blah,
right.
blah, blah.
One point I was making is that if you have these black holes, they evaporate more quickly. So those constraints are very weakened. Right? We saw that even for black holes of very, very large mass, right? They would evaporate in a millisecond. So for a smaller mass, they will evaporate even more quickly. But the full process of the evaporation is, if you want to do more phenomenological study, you have to understand better the infrared dynamics, because when the temperature gets low, well, it depends on what you're discussing. If you're discussing the synthesis, perhaps, well, they're still low, and then you have to understand better the QCD effects. What happens, let's say, QCD corona and so on.
Yeah. And the other thing I just, you mentioned something using like M equal to 2Q or something in the middle of the discussion. It's not a near extremum. It's just something, okay, M equal 2 times Q. And then how to understand this Q factor in that case? Because in that case, you can just treat like not near extremum 4-dimensional black hole. And then Q corresponds, of course, momentum in a XY direction, right? Just a surface. Why it's enhanced by Q in that case?
So in which case, sorry?
Oh, if the mass is like significantly above extremum limit, Q. Oh,
yeah.
Okay, both are Q. But
So the enhancement doesn't have to do with extremality, but it has to do with the magnetic field, the magnetic charge.
Magnetic field. Okay, so potential barrier is not there.
So I was taking a situation where the mass was, let's say, twice the charge. So the magnetic field is still very important, and you still have this factor of Q. And that's what enhances the effect.
So if the electrically charged black hole and you have more or less massless magnetic monopole or something, then those things are
then you would have this effect. But I think if you had massless magnetic monopoles, then the electric description would not be very weakly coupled. Usually the description of the weakly coupled would be this one, the magnetic charge and electrically charged particles.
Yeah, that's right. Yeah. Okay, thanks. no one is asking then one more. You said probably shooting proton and then extract the energies. Is it really?
Yeah.
I mean, if it's shooting a proton that reaches to kind of closer to core, and then quantum gravity will enhance a proton decay, and then does that the particle can go straight? I mean, if it's coming as a Hawking radiation, then it's useless energy extraction, right? I mean, you want to have a GeV to be, 2 particle or 3 particle to be useful.
Yeah. So I think, so the idea is that you send in the protons, and exactly what exactly the cross section is seems complicated to figure out exactly, because it depends on the shape of the QCD corona and exactly what will happen to the protons once they get there. Mm-hmm. Of course, the fact that you have the magnetic field seems to somehow help to concentrate the protons, but most of the radiation. So what you would like to do is to send enough protons so that you get the radiation comes out in electrons, for example, or positrons.
Yeah, not in the form of the Hawking radiation, low temperature thing. I mean, it's just like a 2-body.
Yeah. You don't want it to come out in neutrinos, for example. Yeah, you would like to get it.
Yes.
And but neutrinos don't have this extra enhancement factor of Q because they are not charged. Yeah,
so maybe going to all electron or something, and then just thermalized, and then it's kind of
What you would expect is that in the interior region of so there is this interior of the corona. Within there, you will have some state at some temperature and thermal equilibrium.
Yeah,
and then some of the field, some of the energy will come out of the corona, and then we'll get into the QCD, the region where the QCD vacuum is different, and then eventually some part will come out.
Like but
the precise rates I cannot tell you, but
I had a question on the Blanford. Oh, sorry. Go ahead.
Go ahead.
I had a question when you were talking about the Blanford's Nyack effect. How we should expect these things to generically not be rotating.
Right.
So the idea is that if I try to spin them up, that costs me some extra energy. There's energy flow out to infinity. So if I have one of these objects and it's extremal, I'll be sort of forbidden from having any energy flow out to infinity, right? So if I try and spin it up, basically all the energy, or a large fraction of the energy I'm dumping into trying to spin it up, just ends up being sent out to infinity. So does this act like a restoring force? Like if I try and spin it up, does it try and spin back, or does it just kind of slow down?
Yeah. Well, roughly speaking, So the statement is more precisely that so Kerr-Newman is a stationary solution of the equations of GR plus plus electromagnetism. Kerr-Newman is not a solution of GR plus force-free electromagnetism. And in fact, the idea is that there is no stationary solution. And so if there was a configuration that is kind of like rotating, it will be time dependent and stop rotating.
I see.
So that is the idea.
Thank you.
Of course, in the Blanford-Senyak, so in the actual astrophysical black holes, the magnetic field is not a monopole; it's more like a dipole. So it's a little more complicated, and there is some disk, etc. But the basic picture of the people talk about the magnetic lines getting twisted and so on. So it's this picture of the strings. I mean, it's the same, same picture. I mean, they originally found this picture. So.
I have a question.
Perhaps I can ask a question and Tanmay Vachespati. Juan, there was some discussion of, in the Ambjorn-Olesen case, whether the magnetic field is screened or anti-screened due to the W condensation. Do you have a feeling for that?
Well, I think so I think I would call it screened in the sense that let me see. In the sense that the SU2 part disappears, right? So when the magnetic field is very high, you just get the pure U1 part, not the SU2 part. I saw some of those papers. I have to confess I didn't understand them.
That has always confused me. But is it also clear to you that this corona doesn't have an angular instability of any kind? Is that clear that it will be spherically symmetric?
No, it's not spherically symmetric. So
Okay.
it's not spherically symmetric. It
Because of
it doesn't have a particular symmetry. So it would be like so. I would the idea is that in flat space this you have something that looks a bit like vortices that are forming a triangular lattice. That's roughly what people have discussed. And so you will have this kind of triangular lattice trying to wrap the sphere. You won't be able to do that. So there will be some dislocations and stuff. And that's roughly what I expected.
But it won't collapse to a disk or a kind of on the poles or some.
No, well, the magnetic field tries to be as far, tries to get distributed, right, over the whole sphere. At least intuitively, it seems reasonable to me that this will be stable. But
the vortices might attract too. So, well. Yeah.
Well, if you had vortices of U1, yeah, they might attract or not. But in this case, where there is both magnetic field inside and outside, I think it's convenient for the whole structure to be spread out.
I see. Okay, one last comment. Is that picture in your background one of these black holes?
Well, this is some structure, some curious structure that forms around the black. Oh, this one here. Yeah. No, that's of course the solar corona. But I thought I would have some fun with them.
Good idea.
Right, it works best when you put your head right in the middle. And it
yeah,
like
this.
Yeah, that's. Yeah. Well, I think Masamichi had a question as well.
Oh, yes, I have a question about. So in your traversal wormhole and 4-dimension paper, I remember it's important to have the rotation, a mutual rotation. With
yes.
Doesn't that same mechanism in your talk stop rotation in that case also?
Yes, you are right. But it was a different, and that gives it a finite lifetime. But here we were discussing spin, right, which could be pretty high and so on. In the other case, we were discussing two black holes which were far apart from each other, and so we're rotating relatively slowly through, let's say, more non-relativistic rotation, or planetary. Roughly, it looks like planetary motion. Where we're not thinking of the two. We didn't have the two black holes very close to each other. There were many Schwarzschild radii away from each other. So that was one feature. The second is that one had positive charge, the other one had negative charge. So if there were these strings, most of the strings were going around the wormhole.
Oh, okay, I see.
Coming out of the black hole and going to, and so there were few that were going to infinity, but the few going to infinity would give
I see.
this effect, and we took into account.
The last thing, I could check myself, the factor, but it's quicker to ask. You said there are two phase transition at the W mass and Higgs mass.
Yeah.
But the relevant Higgs mass is a Higgs mass squared, right? Because that's the instability.
Mass squared, yes.
Right, a parameter, mass square parameter. Yes. And then of course, square root 2 and 2 and so on. And if W is 81, what's the value? Is it really 125 or 125 times square root 2 or 125 over square root 2 or?
No, the numbers were without factors of 2. So one is MW squared, the other one is M Higgs squared.
But then it has to be cancelled, right? Then because physical Higgs mass is not a relevant thing. It's a relevant thing is a mass squared parameter, which is at the top, right? So, but you're saying
I see what you're asking. No, it's actually the thing that appears there is actually the mass squared. Well, okay.
Yeah, it can cancel. It can cancel, of course. But
okay, I was discussing the classical theory. So you're right that what is relevant is the mu squared,
Yeah.
And the
yeah.
mu squared is like twice the Higgs mass or half the Higgs mass.
Whatever depends on, yeah.
But there is another half that comes from the fact that the hypercharge has half.
Yeah,
that
okay,
the Higgs
good.
hypercharge has half. And these halves cancel in such a way, or they combine in such a way that the actual value of F is the mass squared.
Yeah. That was the question. Yeah. That's why I said I could check. I could check myself.
Yeah. No,
Okay,
I did check this, and well, people checked it before me.
Yeah, thank you.
Yeah, of course, if you include loop corrections and so on, it's not exactly the same.
Yeah, of course. Yeah, thank you.
Any more questions? If not, let us thank Juan again.
Thank you.
Okay, see you.
Thank you very much.
See you.